Welcome to tonight's journey through the cosmos. We're going to explore our closest celestial neighbor, the Moon, through 100 fascinating facts. Let your mind drift with each revelation. Allow your breathing to slow, and let the wonder of the lunar world carry you gently toward rest. The Moon was born from violence and fire, according to the leading scientific theory. Around 4.5 billion years ago, when Earth itself was still young and molten, a Mars-sized planet wandered through the inner solar system. Scientists call this ancient world Theia, named after the Greek goddess who gave birth to Selene, the goddess of the moon. Based on evidence from lunar samples and computer simulations, Theia appears to have moved through space on a collision course with the early Earth. And when the two worlds met, the impact was beyond imagination. The collision released more energy than all the volcanoes and earthquakes in Earth's history combined. Both worlds were shattered, torn apart by forces that melted rock and vaporized entire regions of planetary crust. The heat was so intense that portions of both planets turned to vapor, creating a cloud of superheated gas and molten debris that surrounded what remained of Earth. This ring of destruction would not last forever. Slowly, over millions of years, gravity began its patient work. Particles collided, stuck together, and grew. Larger pieces attracted smaller ones, and gradually, from the chaos of impact, a new world began to form. The debris coalesced into a sphere, cooling and hardening as it grew. This was the birth of our celestial neighbor, born not from peaceful accretion, but from cosmic catastrophe. The violence of its creation explains many unique characteristics we observe today. Unlike Earth, it has almost no iron core, because the impact threw mostly the outer layers of both worlds into orbit. The intense heat drove away water and other materials that evaporate easily, leaving this new world bone dry. What formed in Earth's orbit was a companion fundamentally different from its parent, yet forever bound to it by gravity's invisible threads. The Moon is smaller than you might imagine. Its diameter stretches just over 3,474 kilometers from edge to edge, roughly 1/4 the width of Earth. If you could place our lunar neighbor next to the continental United States, it would span from coast to coast with room to spare. Yet despite covering an area comparable to the continents of North and South America combined, its total mass is only 1/81st that of Earth. If you could somehow place it on a cosmic scale, you would need 81 moons to balance a single Earth. This smaller size means weaker gravity. On the lunar surface, you would weigh only about 1/6 of your Earth weight. A person who weighs 180 pounds on our planet would tip the scales at merely 30 pounds up there. This is why the Apollo astronauts could leap so high, despite wearing heavy spacesuits packed with life support equipment. Each step became a gentle bound, and movements that would be ordinary on Earth transformed into graceful, floating motions in the diminished gravity. The lunar surface stretches across 38 million square kilometers, a vast expanse of craters, mountains, and ancient lava plains waiting to tell their stories. Lunar density tells us about its internal structure. At 3.34 grams per cubic centimeter, this world is considerably less dense than Earth, which weighs in at 5.5 grams per cubic centimeter. This difference reveals a lack of the heavy iron core that dominates Earth's interior. Instead, if a core exists at all, it is tiny, perhaps only 240 kilometers across at its innermost point, surrounded by a fluid outer core of liquid iron roughly 300 kilometers in radius. Most of the mass comes from rocky mantle and crust, materials similar in composition to Earth's outer layers. This structure formed during an early molten phase when heavier materials sank toward the center while lighter rocks floated to the surface, creating the layered world we see today. The lack of a substantial iron core also means no global magnetic field, like Earth's protective shield exists. Some lunar rocks do show traces of ancient magnetism, suggesting our companion may have once possessed a magnetic field billions of years ago, perhaps generated by a molten core that has since cooled and solidified. Our satellite always shows us the same face. This phenomenon, called tidal locking, means it rotates on its axis at exactly the same rate it completes one orbit around Earth, taking roughly 27.3 days for each. As a result, one hemisphere perpetually faces our planet, while the other remains forever hidden from Earth-based observers. This synchronization did not happen by chance. Over millions of years, Earth's gravity pulled on slight bulges in its shape, creating tidal forces that gradually slowed the rotation until it matched the orbital period. The near side, the face we see each night, has been mapped and studied for centuries. Ancient astronomers noted its dark patches and bright regions, imagining faces and figures in the patterns of light and shadow. The far side remained a mystery until October 1959, when the Soviet spacecraft Lunar 3 swung around our satellite and transmitted the first grainy images of the far side back to Earth. What those images revealed surprised scientists. The far side looked dramatically different, with far fewer of the dark plains called Maria and many more heavily cratered highlands. This difference remains one of the enduring mysteries, a puzzle written in rock and crater that scientists are still working to fully understand. Several theories attempt to explain this asymmetry. The far side crust appears to be thicker, based on gravitational measurements, which could make it harder for lava to reach the surface and fill impact basins. Another possibility involves Earth's gravitational influence during the period of volcanic activity, perhaps concentrating eruptions on the near side. The true explanation likely involves multiple factors interacting in ways researchers continue to investigate. The Moon drifts slowly away from Earth. Each year, the Moon's orbit carries it approximately 3.8 centimeters farther from our planet. This gradual recession happens because of tidal forces, as the Moon's gravity pulls on Earth's oceans, creating the tides that rise and fall along our coastlines. Friction between the moving water and the ocean floor acts like a brake on Earth's rotation. This stolen rotational energy doesn't disappear. It transfers to the Moon, giving it a tiny boost that pushes its orbit slightly higher. Over vast spans of geological time, this effect is substantial. When dinosaurs walked the Earth, the moon loomed larger in the sky, and Earth spun faster, making days shorter than they are now. Looking forward, the moon will continue its outward journey for billions of years, growing smaller in our sky as the distance between our two worlds increases. The same process has already slowed Earth's rotation significantly. Days have been growing longer throughout Earth's history, and this lengthening continues at a rate of about 2 milliseconds per century. The moon and Earth are locked in an ancient dance, each partner slowly changing the other through the invisible but inexorable pull of gravity. The moon's phases follow a predictable cycle. As the moon orbits Earth every 29.5 days, we see different portions of its sunlit surface, creating the phases that have marked time for civilizations throughout history. The cycle begins with the new moon, when the moon passes between Earth and the sun, presenting its dark side to us and becoming invisible in the sun's glare. Then a thin crescent appears, growing night by night through the waxing crescent phase as more of the sunlit surface becomes visible. After roughly a week, half the moon is illuminated in what we call the first quarter, though it marks 1/4 of the way through the cycle, not half the moon's surface. The illumination continues to grow through the waxing gibbous phase, and finally the full moon arrives, the entire face we see bathed in sunlight. After that peak, the process reverses. The light diminishes through waning gibbous to third quarter, when again half the face shines, then wanes further through the crescent phase, until returning to new moon and beginning the cycle again. These phases happen because the moon produces no light of its own. What we see is sunlight reflecting off its surface, and as the moon's position relative to Earth and sun changes, so does the portion of that reflected light reaching our eyes. The moon's phases have guided human activity for millennia. Ancient peoples used the lunar cycle to track time, creating calendars based on the moon's predictable journey through its phases. The word month itself derives from moon, reflecting this deep connection between lunar cycles and human timekeeping. Many cultures scheduled festivals, religious observances, and agricultural activities according to the moon's phases. Farmers knew when to plant and harvest. Fishermen understood how the phases affected tides and fish behavior, and travelers navigated by moonlight, planning journeys to take advantage of the full moon's illumination. Different phases acquired names reflecting seasonal activities and natural events. The harvest moon, the full moon nearest the autumn equinox, provided extra light for farmers gathering crops. The hunter's moon followed, lighting the way for hunting expeditions. Cold moon, snow moon, worm moon, each name told a story about the time of year and the activities it brought. Even today, despite electric lights and digital calendars, the moon's phases continue to mark time in ways subtle and profound, a living connection to the rhythms that shaped human culture. The moon's surface is covered in craters. Billions of years of bombardment by asteroids, comets, and meteoroids have left the lunar landscape pockmarked with impact scars of every size imaginable. Some craters span just meters across, tiny dimples created by pebble-sized impacts. Others stretch hundreds of kilometers, massive basins excavated by collisions with mountain-sized asteroids. Each crater tells a story written in violence and preserved in stone. The largest craters, called impact basins, were formed during a period called the Late Heavy Bombardment, roughly 3.9 billion years ago, when the inner solar system experienced a surge of impacts. These titanic collisions shattered the lunar crust, creating vast depressions that would later fill with lava to become the dark Maria we see today. The moon's craters remain pristine because it lacks the weathering processes that erase such features on Earth. There is no wind to fill them with dust, no rain to erode their edges, no tectonic activity to fold them into mountains. The oldest craters, billions of years old, look almost as fresh as those formed yesterday. Walking on the lunar surface, an astronaut sees evidence of impacts from every era of solar system history, a geological record preserved in airless silence. The dark patches on the moon are ancient lava plains. These regions, called Maria, the Latin word for seas, were named by early astronomers who thought they might be bodies of water. In reality, they are vast basaltic plains created by enormous volcanic eruptions billions of years ago. The Maria formed when massive asteroid impacts fractured the lunar crust, allowing molten rock from deep within the moon to well up and flood the impact basins. This lava was remarkably fluid, flowing for vast distances before cooling and hardening into the smooth, dark basalt we see today. The Maria make up only about 15% of the moon's surface, concentrated mostly on the near side facing Earth. Mare Imbrium, the Sea of Rains, spans roughly 1,100 kilometers across, making it one of the largest. Mare Tranquillitatis, the Sea of Tranquility, earned its place in history when Apollo 11 landed there in 1969. The Maria appeared darker than the surrounding highlands because basalt reflects less light than the brighter rock of the highland regions. These ancient lava flows provide scientists with invaluable information about the moon's volcanic past and the composition of its interior, frozen moments of the moon's active geological youth preserved across billions of years. Between the Maria lie the lunar highlands. These bright, heavily cratered regions are the moon's oldest terrain, original crust that formed when the young moon's surface cooled and solidified. The highlands are composed primarily of a rock called anorthosite, a light-colored igneous rock rich in aluminum. This rock formed when the moon was covered by a vast ocean of molten rock, and lighter minerals floated to the surface like cream rising in milk. The highlands stand roughly 4 to 5 kilometers above the average lunar surface elevation, while the Maria sit 2 to 3 kilometers below, creating the relief that gives the moon its varied appearance. The heavy cratering in the highlands shows their great age. These regions have been exposed to impacts for billions of years, accumulating scars from countless collisions. Some highland areas show such dense cratering that they approach what scientists call saturation, where the surface is so covered with craters that new impacts destroy old ones at the same rate they're created, leaving the total crater density unchanged. Studying the highlands helps scientists understand the Moon's earliest history and the conditions that prevailed when the solar system was young and chaotic. The Moon's surface is covered in regolith. This layer of loose, fragmented material blankets almost the entire lunar surface, created by billions of years of meteoroid bombardment. Each impact, whether from a massive asteroid or a grain of dust moving at hypervelocity, chips away at the bedrock, slowly grinding it into ever finer particles. The regolith varies in thickness from place to place. In the young Maria, it may be only a few meters deep, while in the ancient highlands it can extend 20 meters down or more. The material ranges from house-sized boulders to powder finer than sand, all mixed together in a layer that crunches and shifts under footsteps. The Apollo astronauts described it as having a texture like wet sand, despite being completely dry. The finest particles electrostatically cling to everything, covering spacesuits, equipment, and even managing to infiltrate sealed containers. The regolith contains more than just ground-up moon rock. Mixed into it are fragments of meteorites from throughout the solar system, each impact contributing a tiny sample of its parent body to the lunar soil. This makes the regolith a natural archive, a collection of solar system materials accumulated over eons and preserved in the lunar vacuum. The Moon's lack of atmosphere makes it a harsh environment. Unlike Earth, protected by layers of air that filter radiation, moderate temperature, and burn up incoming meteors, the Moon faces space directly. Surface pressure measures only about 3 times 10 to the negative 15 atmospheres, essentially a perfect vacuum. What little gas exists comes from solar wind particles, radioactive decay in lunar rocks, and the rare impact of a comet. This thin exosphere, as scientists call it, contains atoms of helium, neon, argon, and traces of other elements. But it's far too tenuous to be called an atmosphere. At these densities, about 80,000 atoms per cubic centimeter, the atoms don't collide with each other. They simply move in ballistic trajectories until they either escape to space or freeze onto the cold nighttime surface. The absence of atmosphere has profound consequences. There is no weather on the Moon, no wind, no clouds, no rain. The sky remains black even during the lunar day because there's no air to scatter sunlight. Temperatures swing wildly between day and night, from about 127 degrees Celsius in direct sunlight to negative 173 degrees Celsius in shadow, a range of 300 degrees that would shatter most materials on Earth. The Apollo program brought 12 humans to the Moon. Between 1969 and 1972, NASA conducted 6 successful lunar landing missions, each one expanding our knowledge of Earth's nearest neighbor. Apollo 11 made history on July 20, 1969, when Neil Armstrong and Buzz Aldrin became the first humans to walk on another world while Michael Collins orbited above in the command module. Armstrong's first words as he stepped onto the lunar surface have echoed through decades. That's one small step for man, one giant leap for mankind. Apollo 12 landed in the ocean of storms just 4 months later, demonstrating that the first landing was no lucky accident. Apollo 13 never reached the surface after an oxygen tank explosion forced the crew to loop around and return to Earth in their damaged spacecraft, a near disaster that became a triumph of improvisation and determination. Apollo 14 explored the Fra Mauro Highlands. Apollo 15 introduced the lunar rover vehicle, allowing astronauts to travel kilometers from their landing site. Apollo 16 investigated the Descartes Highlands, and Apollo 17, the final mission, brought geologist Harrison Schmitt, the only scientist to walk on the moon. These 12 moonwalkers collected 842 pounds of lunar rocks and soil, conducted experiments, deployed scientific instruments, and proved that humans could work effectively in the alien lunar environment. The lunar samples transformed our understanding. Rocks brought back by Apollo missions range from 3.1 to 4.4 billion years old, providing direct evidence of the moon's ancient history. Analyzing these samples revealed that our lunar companion formed between 60 and 175 million years after the solar system's birth, supporting the giant impact hypothesis. The rocks showed clear signs of having been molten, consistent with what scientists call the magma ocean theory of lunar formation, in which the young satellite's surface was once entirely or largely molten. Chemical analysis found that lunar rocks contained virtually no water and very few volatile compounds, elements that evaporate at low temperatures, as if they had been baked in an oven. The oxygen isotope ratios in lunar rocks matched those found in Earth rocks almost exactly, a striking similarity suggesting the Moon and Earth formed from the same material or that they mixed thoroughly during formation. Some lunar rocks were unlike anything found on Earth. Creep basalts, rich in potassium, rare earth elements and phosphorus, provided clues about the Moon's interior composition. Breccias, rocks made of fragments welded together by impacts, showed the violence of the bombardment that shaped the lunar surface. These samples continue to yield discoveries more than 50 years after collection, as new analytical techniques reveal secrets locked in ancient lunar stone. The Moon creates tides on Earth. As the Moon orbits our planet, its gravitational pull tugs on Earth's oceans, creating the rhythmic rise and fall of sea level we call tides. The mechanism is subtle but powerful. The Moon's gravity pulls strongest on the side of Earth closest to it, less strongly on Earth's center, and weakest on the far side. This difference, called a tidal force, stretches Earth slightly into an oval shape, creating two bulges of water, one facing the Moon and one on the opposite side. As Earth rotates beneath these bulges, any given coastal location experiences two high tides and two low tides each day as it passes through the bulges and the low points between them. The Sun also contributes to tides, though its effect is only about half as strong as the Moon's, despite the Sun being much more massive. Distance matters more than mass for tidal forces, and the Moon's proximity gives it the dominant role. When the Sun, Moon, and Earth align during new moon or full moon, their gravitational forces combine to create especially strong spring tides with higher highs and lower lows. When they form a right angle during quarter moons, the sun's gravity partially cancels the moon's, producing weaker neap tides. Tides affect more than just coastlines. They have been shaping our planet throughout geological history. Tidal forces have been slowing Earth's rotation. The friction between tidal bulges and Earth's ocean floors acts as a brake on our planet's spin. This tidal friction has been gradually lengthening Earth's days throughout geological time. When the moon first formed, orbiting much closer to Earth than today, days were perhaps only 5 hours long. As the moon's gravity raised enormous tides on the young, molten Earth, the tidal friction was even stronger than today, rapidly slowing Earth's rotation and pushing the moon outward. This process continues today at a rate of about 2 milliseconds added to Earth's day length every century. Too small to notice in a human lifetime, but significant over geological ages. Studying growth rings in ancient corals and sediment layers called tidal rhythmites allows scientists to count days in ancient years, confirming that days were shorter in the past. 400 million years ago, during the Devonian period, a year contained about 400 days, each lasting roughly 22 hours. The Earth-Moon system has been exchanging energy for billions of years, with Earth's rotation gradually slowing while the Moon drifts farther away. And this process will continue for billions of years more, until both worlds become tidally locked to each other, forever showing the same face and spinning at the same rate. The Moon has no global magnetic field today. Unlike Earth, which generates a powerful magnetic field through the motion of molten iron in its core, the Moon has at most a very weak field, less than 1/100th the strength of Earth's. However, ancient lunar rocks tell a different story. Some samples collected by Apollo missions show strong remnant magnetism, preserved from a time billions of years ago when the Moon apparently possessed a substantial magnetic field. This suggests the young Moon had a liquid, convecting core capable of generating a magnetic field through the same dynamo process that powers Earth's field. The field may have lasted for several 100 million to 1 billion years before the core cooled and solidified, ending the dynamo action. The loss of the magnetic field left the Moon vulnerable to the solar wind, charged particles streaming from the Sun that can now impact the lunar surface directly. On Earth, our magnetic field deflects these particles, creating the beautiful auroras near the poles. On the Moon, solar wind particles impact the regolith directly, gradually darkening the soil and implanting atoms that wouldn't otherwise be there. Understanding why the Moon lost its magnetic field helps scientists better understand planetary evolution and the factors that determine whether a world can maintain the protective shield that makes it more hospitable to life. There is water on the Moon. For decades, scientists believed the Moon was completely dry, its formation in the searing heat of the giant impact having driven off all volatile compounds. However, observations from spacecraft and analysis of lunar samples have revealed a more complex picture. In 1998, NASA's Lunar Prospector detected hydrogen signatures near the lunar poles, suggesting the presence of water ice in permanently shadowed craters. These cold traps, where sunlight never reaches, maintain temperatures cold enough to preserve ice for billions of years. Subsequent missions have confirmed these findings. The impact of the L-Cross spacecraft in 2009 raised a plume of debris from a polar crater that spectroscopic analysis showed contained water. The concentration isn't vast, with some measurements suggesting up to 5 to 8% water content in the soil of certain permanently shadowed regions, though this varies by location. More surprisingly, scientists have detected small amounts of water, perhaps just a few parts per million, distributed across much of the lunar surface, even in areas exposed to sunlight. This water likely comes from hydrogen atoms in the solar wind, combining with oxygen in lunar minerals, or from water-bearing micrometeorites continually pelting the surface. The presence of water, even in small quantities, changes how we think about the Moon's history and its potential to support human exploration. The Moon experiences moonquakes. Although generally quieter than Earth, with no plate tectonics or volcanic activity, the Moon is not completely geologically dead. Seismometers left by Apollo astronauts detected thousands of moonquakes during their years of operation. These quakes fall into 4 categories. Deep moonquakes occur roughly 700 kilometers below the surface, likely caused by tidal forces as Earth's gravity needs the Moon's interior. These happen regularly at specific depths when the Moon reaches certain points in its orbit. Thermal moonquakes occur when the frigid lunar night transitions to the searing daytime heat, causing surface materials to expand and crack. Meteor impacts create brief but powerful seismic signals as rocks from space slam into the airless surface. Most intriguingly, shallow moonquakes occurring just 20 to 30 kilometers deep can be surprisingly strong, with some reaching magnitudes around 5 on the Richter scale and lasting over 10 minutes, far longer than earthquakes of similar strength. The reason moonquakes last so long is that the Moon's crust is extremely dry and rigid, lacking the water and complex fault systems that dampen seismic energy on Earth. When moonquakes occur, the whole Moon rings like a bell, vibrations bouncing back and forth through the interior for extended periods, before finally dissipating into silence. Analysis of high-resolution images from NASA's Lunar Reconnaissance Orbiter has revealed thousands of relatively young cliff-like features called thrust faults scattered across the lunar surface. These faults form when the crust crumples, pushed together as the interior continues its slow cooling and contracting. Research suggests our companion has shrunk by approximately 150 feet in circumference over the shallow, past several 100 million years, and this process continues today. As the interior cools, it occupies less volume, and the rigid outer crust must accommodate this change by fracturing and folding. The process is similar to what happens to a grape as it dries into a raisin, developing wrinkles on its surface. Some of these faults are very young, perhaps less than 50 million years old, suggesting the Moon remains a dynamic world, despite having no active volcanism or plate tectonics. The stress from this ongoing shrinkage may trigger some of the shallow moonquakes detected by seismometers, linking the Moon's seismic activity to its thermal evolution. Understanding this process helps scientists piece together the moon's interior structure and thermal history, revealing how planetary bodies cool and evolve over billions of years. Ancient peoples knew the moon intimately. Before electric lights washed out the night sky, the moon was a dominant presence in human awareness. Every culture developed myths and stories to explain its presence, its phases, and its movements. Many saw the moon as a deity, a powerful force governing night, tides, and the passage of time. The Mesopotamians associated the moon with the god Sin, Greeks with Selene and Artemis, Romans with Lunar, Egyptians with Thoth and Khonsu. Chinese mythology spoke of Chang'e, who drank an elixir of immortality and floated to the moon, where she resides forever with her jade rabbit companion. In Japan, people saw a rabbit pounding mochi in the patterns of the Maria. Indigenous peoples of the Americas wove the moon into creation stories and used its cycles to mark seasons and plan hunts and harvests. The moon's reliable phases made it a natural timekeeping device. Many ancient calendars were lunar, measuring months by the moon's cycle from new to full and back. Even today, several major religious calendars, including Islamic and Hebrew calendars, remain primarily lunar, with months beginning at the sighting of the new crescent moon. This ancient relationship between humans and moon shaped culture, religion, art, and science for millennia, before the first telescope ever pointed skyward. Eclipses occur when sun, moon, and Earth align. A lunar eclipse happens when Earth passes directly between the sun and moon, casting its shadow onto the lunar surface. From the moon's perspective, Earth would block the sun, and the moon enters Earth's cone of shadow trailing behind our planet. These events can only occur during full moon, when the three bodies are in the correct geometric alignment. There are three types of lunar eclipses. During a penumbral eclipse, the moon passes through Earth's faint outer shadow, causing only subtle dimming that many people don't notice. A partial eclipse occurs when part of the moon enters Earth's darker umbral shadow, creating a visible shadow creeping across the lunar face. A total lunar eclipse, the most spectacular, occurs when the entire moon enters the umbra. Rather than disappearing, the moon takes on a deep red or coppery color, earning the name blood moon. This happens because Earth's atmosphere acts like a lens, bending some sunlight around the planet. Blue light scatters away, while red light refracts through the atmosphere and onto the moon. The same phenomenon that creates red sunrises and sunsets. Ancient peoples sometimes feared lunar eclipses, seeing them as omens or attacks on the moon by celestial dragons. Modern understanding has removed the supernatural dread, but preserved the wonder. Total lunar eclipses remain beautiful spectacles, turning the moon's familiar silver glow into an eerie crimson sphere hanging in the night sky. Solar eclipses reveal a cosmic coincidence. Although the sun is 400 times larger than the moon, it also happens to be roughly 400 times farther away. This coincidence makes the sun and moon appear almost exactly the same size in Earth's sky. When the moon passes directly between Earth and Sun, it can precisely block the solar disk, creating a total solar eclipse. For a few minutes, day turns to twilight, stars appear, and the Sun's outer atmosphere, the corona, becomes visible as a pearly halo around the dark lunar silhouette. This perfect size matching is temporary. Because the moon is slowly moving away from Earth, it appears slightly smaller in our sky with each passing millennium. In the distant past, the moon was larger in the sky and total eclipses lasted longer. In the far future, the moon will appear too small to completely cover the sun, and total solar eclipses will become impossible, replaced only by annular eclipses where a ring of sunlight remains visible around the moon's edges. We live in a special time in Earth's history when these perfect solar eclipses can occur. Ancient observations of solar eclipses helped astronomers understand celestial mechanics. The Greek philosopher Anaxagoras used a solar eclipse to correctly explain that the moon shines by reflected sunlight and eclipses occur when celestial bodies cast shadows on one another. These events demonstrated that the heavens followed predictable laws, helping transform astrology into astronomy. The moon's orbit is not circular. Like all orbits, the moon's path around Earth traces an ellipse, a slightly squashed circle. At its closest point, called perigee, the moon comes within about 357,000 kilometers of Earth. At its farthest point, apogee, it recedes to roughly 407,000 kilometers. This variation of about 50,000 kilometers means the moon's apparent size in our sky changes by about 14% from smallest to largest, and its brightness can vary by about 30%. When a full moon coincides with perigee, creating what media outlets have dubbed a supermoon, the moon appears noticeably larger and brighter than usual. These enhanced full moons happen several times each year, but rarely receive special attention from astronomers who have known about perigee and apogee for centuries. The varying distance also affects tides, with perigee bringing slightly stronger tides and apogee resulting in weaker ones. The moon's orbit doesn't maintain the same orientation over time either. The ellipse itself slowly rotates, its major axis tracing a full circle every 9 years. This precession combines with other orbital variations to create complex patterns in the moon's position that ancient astronomers painstakingly mapped, leading to the development of sophisticated mathematical models of lunar motion. The moon's far side remained hidden until the space age. Before 1959, no human eyes had ever glimpsed the face of the moon that perpetually turns away from Earth. Tidal locking ensures that the same hemisphere always faces our planet, making the far side forever invisible to earthbound observers. Ancient astronomers could only imagine what lay beyond the visible edge, and some speculated about alien civilizations or strange phenomena hidden from our view. The mystery ended on October 7, 1959, when the Soviet probe Lunar 3 swung around the moon and transmitted the first grainy images of the far side back to Earth. What those pictures revealed surprised scientists. The far side looked dramatically different from the near side, with far fewer of the dark maria and a much more heavily cratered surface. This asymmetry remains puzzling. Several theories have been proposed to explain it. The far side crust may be thicker, making it harder for lava to reach the surface and fill impact basins. The far side was less protected from impacts during the late heavy bombardment. Earth's gravity may have influenced where volcanic activity occurred. The true explanation likely involves multiple factors. The far side receives the same amount of sunlight as the near side, so calling it the dark side is a misnomer, though the phrase has persisted in popular culture, perhaps because it was mysterious and unknown for so long, hidden from human knowledge if not from the sun's light. Our companion influences Earth's climate stability. While the sun obviously drives Earth's climate through its energy input, the gravitational presence of our satellite plays what researchers believe to be an important role in maintaining long-term climate stability. The gravitational influence appears to help stabilize Earth's axial tilt, the angle at which our planet's rotation axis leans relative to its orbital plane. Earth currently tilts about 23.5 degrees, and this tilt creates our seasons. Summer happens when your hemisphere leans toward the sun. Winter when it leans away. Computer simulations of Earth without a large moon show that, over millions of years, gravitational tugs from other planets, especially Jupiter, could cause Earth's axial tilt to vary significantly, perhaps swinging between nearly 0 and more than 60 degrees. Such dramatic changes would create extreme climate variations, with ice ages and hot periods cycling far more rapidly and severely than Earth has experienced. The mass and proximity of our satellite create enough gravitational torque to help dampen these variations, keeping Earth's tilt relatively stable within a range of about 22 to 24.5 degrees over tens of millions of years. Mars, which has 2 tiny moons with negligible gravitational influence, shows evidence of past tilts ranging widely, potentially contributing to its loss of atmosphere and surface water. The Moon affects Earth's rotation period. We've discussed how tidal friction slows Earth's spin, but this effect has implications beyond just lengthening days. In Earth's early history, when the planet rotated much faster, it experienced powerful atmospheric circulation patterns we can only imagine. Storm systems would have been more intense, and weather patterns dramatically different from today. As Earth's rotation slowed, ocean currents, atmospheric circulation, and climate patterns all evolved. The slowing continues today, imperceptible in human lifetimes, but measurable with atomic clocks and precise observations. Modern timekeeping must occasionally add leap seconds to keep clock time synchronized with Earth's rotation, which doesn't match the precise ticking of atomic clocks. These leap seconds compensate for the gradual slowdown caused primarily by lunar tides. Earth's day now lengthens by about 2 milliseconds per century, a tiny amount that accumulates to significant change over millions of years. Looking back, we can calculate that roughly 400 million years ago, during the Devonian period, a year contained about 400 days of approximately 22 hours each. Fossil evidence from ancient corals and stromatolites supports these calculations, showing growth patterns that reflect the shorter days and longer years of ancient times. The Moon has been our constant companion, not just in space, but in time. Its gravitational pull slowly but inevitably reshaping how our planet spins through the cosmos. Our celestial neighbor may have had an atmosphere, not today and not recently, but in the distant past. The young world might have temporarily possessed a thin atmosphere. During the period of intense volcanic activity that created the Maria, roughly 3 to 4 billion years ago, volcanic eruptions would have released gases from the interior. The eruption rates were enormous, perhaps orders of magnitude greater than the largest volcanic events on Earth. Computer models suggest these eruptions could have released water vapor, carbon monoxide, sulfur compounds, and other volatiles faster than they escaped to space, potentially creating a temporary atmosphere. This atmosphere might have lasted for 70 million years or more, gradually leaking away into space as volcanic activity declined and weak gravity proved insufficient to hold on to the gases long term. During this hypothetical interval in lunar history, surface pressure might have reached 1.5% of Earth's current atmospheric pressure, enough that liquid water could theoretically exist on the surface, at least in some locations under the right conditions. Evidence for this ancient atmosphere remains speculative, based primarily on volcanic output estimates and atmospheric escape models. If it existed, it would have been visible from Earth, the young satellite glowing not with reflected sunlight alone, but with the fires of volcanic eruptions, surrounded by a hazy envelope of gas that would eventually thin and vanish, leaving the airless world we know today. The Moon preserves a record of solar system history. Because it lacks atmosphere, weather, oceans, and active geology, the Moon's surface remains remarkably unchanged over billions of years. Impact craters that would erode away on Earth in mere millions of years remain pristine on the Moon for eons. This makes the lunar surface a natural archive, preserving a record of impacts throughout solar system history. By studying the number and size distribution of craters on different lunar surfaces, and combining this with radiometric dating of rocks from those surfaces, scientists can establish a chronology of impact rates over time. This chronology then helps date surfaces on other worlds. If a region on Mars or Mercury has a similar crater density to a dated lunar surface, it probably formed around the same time. The Moon essentially provides a calibration curve for dating planetary surfaces throughout the inner solar system. The lunar impact record shows that the rate of large impacts was much higher early in solar system history, declining rapidly after the first billion years as the planets cleared their neighborhoods of debris. Occasional spikes in the impact rate may represent periods when asteroid collisions or cometary showers sent more projectiles toward the inner planets. Every crater on the Moon is a moment frozen in time, a visitor from space that left its mark on the lunar landscape. Together, these countless scars tell the story of a violent solar system gradually becoming quieter as order emerged from primordial chaos. Our neighbor could be a future resource. As humanity looks toward establishing a permanent presence beyond Earth, this nearby world offers several advantages. Its proximity, just 3 days away by spacecraft, makes it more accessible than any other celestial body. The presence of water ice in polar craters could provide drinking water for astronauts, and when split into hydrogen and oxygen, could supply breathable air and rocket propellant. Lunar regolith contains metals like titanium and iron, silicon for solar panels and computer chips, and rare earth elements useful in electronics. Helium-3, a rare isotope on Earth but relatively abundant in lunar regolith after billions of years of solar wind bombardment, has been proposed as potential fuel for fusion reactors if that technology becomes practical, though this remains speculative and faces significant technical hurdles. The Moon's low gravity, 1/6 of Earth's, makes it far easier to launch spacecraft from the surface, potentially making the Moon a staging ground for missions to Mars and beyond. Lunar bases could support astronomical observatories taking advantage of the stable surface, lack of atmosphere, and long periods of darkness. The far side of the Moon would be shielded from Earth's radio interference, making it ideal for sensitive radio telescopes searching for faint signals from the early universe. Several nations and private companies are planning lunar missions, from robotic landers to crewed bases, envisioning a future where the Moon transforms from a destination to a port, a way station in humanity's expansion into the solar system. Our companion is moving away, but will eventually stop. Currently, it recedes from Earth at about 3.8 centimeters per year, pushed outward by the transfer of Earth's rotational energy through tidal interactions. This process will not continue forever. Eventually, in a theoretical future tens of billions of years from now, Earth's rotation would slow until one day equals about 47 of our current days. At that point, Earth and its satellite would be mutually tidally locked, always showing the same face to each other, with the satellite hanging motionless in the sky as viewed from one hemisphere while remaining forever invisible from the other. When this configuration is reached, the tidal bulges would no longer move relative to Earth's surface. Tidal friction would cease, and the outward drift would stop. This represents the system's equilibrium state, roughly 30% farther than today's orbit. However, as we've discussed, the Sun's evolution into a red giant will intervene long before this mutual locking could occur, making this endpoint a theoretical curiosity rather than an actual future. The Moon lacks plate tectonics. On Earth, the surface constantly renews itself through plate tectonics, where the crust breaks into pieces that move, collide, and sink back into the mantle. This process recycles rock, builds mountains, triggers earthquakes, and drives volcanic activity. The Moon has no such system. Its crust formed billions of years ago and remains largely frozen in place, a solid shell wrapped around the interior. Without plate tectonics, the Moon lacks many features common on Earth. There are no spreading ridges where new crust forms, no subduction zones where old crust disappears, no transform faults sliding past each other. The lunar mountains that exist formed primarily from impact processes, crater rims pushed up during basin formation, not from tectonic collisions like Earth's Himalayas or Andes. This geological stillness means that once the period of volcanic activity ended, roughly 3 billion years ago, The Moon's surface features became essentially fixed. Later impacts have added new craters and modified existing features, but no process exists to erase or recycle old surfaces as happens on Earth. Scientists continue to debate whether our satellite ever experienced anything like plate tectonics. Some researchers interpret certain features in very ancient lunar surfaces as possible signs of early tectonic-like activity during the molten phase, but the evidence remains inconclusive. If any such processes existed, they would have ceased within the first few 100 million years of lunar history. The Moon's small size worked against maintaining active geology. Smaller bodies cool faster, their internal heat dissipating more quickly relative to their volume. And once that heat engine shut down, geological activity largely ceased, freezing the Moon in ancient configuration. The Moon's brightness changes beyond just phases. Even when the Moon is full, its brightness varies depending on several factors. Distance plays a role. Perigee full moons appear about 30% brighter than apogee full moons due to the closer distance and slightly larger apparent size. The Moon's brightness also depends on how long it has been since the last full moon, due to a phenomenon called the opposition effect. When the Sun is directly behind the observer, hitting the Moon straight on, shadows disappear and the surface appears brighter than when viewed at an angle. This makes full moons especially bright, compared to gibbous moons that are almost but not quite full. The Moon's surface has varying reflectivity, with dark Maria reflecting only about 7% of incident light, while bright highlands might reflect up to 18%. The overall average reflectivity, called albedo, is only about 12%, making the Moon actually quite dark, darker than worn asphalt. It appears bright to us only because it's so close, and because the night sky is dark by comparison. The Moon's brightness has practical effects on Earth. Full moons provide enough light for humans to see clearly at night without artificial illumination. Many animals use moonlight to navigate, hunt, or avoid predators. Some species synchronize their reproductive cycles with lunar phases using the regular cycle of moonlight as a cue. Before artificial lighting transformed the night, moonlight was a significant factor in human activity, enabling travel and work that would be impossible in the darkness of a new moon. The Moon rotates at exactly the right speed. The fact that pull at the Moon's rotation period matches its orbital period is no coincidence, but rather the inevitable result of tidal locking. When the Moon first formed, it likely rotated much faster, completing a spin in just a few hours rather than the current 27.3 days. However, the Moon was never perfectly spherical. Tidal forces from Earth raised slight bulges on the Moon, making it slightly football-shaped with the long axis pointing toward Earth. As the Moon rotated, these bulges moved relative to Earth, and Earth's gravity pulled on them, creating torque that acted to slow the rotation. Over millions of years, this tidal braking slowed the Moon's spin until it reached the current configuration where the rotation rate matches the orbital rate, keeping the same face toward Earth. Once locked, the bulges remain aligned with Earth, no longer moving relative to it, so the torque disappears, and the configuration becomes stable. This process is not unique to the Moon. Most large moons in the solar system are tidally locked to their parent planets. The process works in both directions, and Earth's rotation is gradually slowing toward becoming locked to the Moon, though this will take billions of years. Tidal locking is gravity's way of finding equilibrium, a natural consequence of gravitational forces acting over geological timescales. The Moon's perfectly synchronized dance, showing one eternal face to Earth, is mathematics and physics expressed through cosmic motion. The Moon's surface is extremely ancient. The youngest lunar rocks collected by Apollo astronauts are over 3 billion years old, formed during the tail end of the volcanic activity that created the Maria. The oldest samples date back about 4.5 billion years, nearly to the solar system's formation. Walking on the Moon, an astronaut stands on surfaces that formed when Earth was young and lifeless, when the solar system was still clearing itself of debris, when the universe itself was significantly younger than it is today. The Moon's ancient surface preserves features from this early era that Earth's active geology has long since erased. The intense crater saturation in highland areas records the late heavy bombardment, a period about 3.9 billion years ago when impacts surged throughout the inner solar system, perhaps triggered by orbital migrations of the giant planets. Earth suffered the same bombardment, impacts energetic enough to vaporize oceans and sterilize the surface, potentially destroying any life that might have emerged earlier. The Moon's face shows us this violent history that Earth experienced but no longer displays. Studying these ancient surfaces helps scientists understand not only the Moon's history, but Earth's as well, revealing the environmental conditions under which life had to emerge and survive. Every ancient lunar landscape is a window into deep time, a preserved moment from an era when the solar system was fundamentally different than the calmer place we inhabit today. The Moon may host future observatories. The lunar environment offers unique advantages for certain types of astronomical observations. The lack of atmosphere means no atmospheric distortion, light pollution only from Earthshine on the near side, and perfect vacuum allowing observations at wavelengths that Earth's atmosphere blocks. The Moon's slow rotation provides our 14 days of continuous darkness, unlike Earth's 12-hour nights, allowing extended observation periods without day-night interruptions. Telescopes on the lunar far side would be completely shielded from Earth's radio emissions, making it the quietest radio environment in the inner solar system, ideal for detecting faint signals from the early universe or searching for technosignatures from extraterrestrial civilizations. The Moon's surface is seismically stable compared to Earth's, with only minor moonquakes providing a solid foundation for precision instruments. Gravity, though lower than Earth's, is still sufficient to simplify construction compared to space-based telescopes that must maintain position against the Sun's pressure and gravitational perturbations. Challenges include the extreme temperature variations, the need to protect instruments from lunar dust, and the difficulty of maintaining and repairing equipment on the Moon's surface. Despite these obstacles, several plans for lunar telescopes exist, from small robotic instruments that could deploy in the next decade to ambitious proposals for massive radio arrays or optical interferometers that would require significant human infrastructure. The moon could become not just a stepping stone for human exploration, but a platform for unprecedented scientific discovery. Eyes on the cosmos built with lunar resources and maintained by human presence, extending our gaze deeper into space and time than ever before. The moon causes more than just ocean tides. While the ocean tides are the most visible effect of the moon's gravity, tidal forces affect the entire Earth. The solid Earth itself rises and falls by about 30 centimeters twice daily as the planet responds to lunar and solar tides, a phenomenon called Earth tides or body tides. We don't notice this because everything rises together, ground and structures alike. These solid Earth tides are measured by sensitive instruments and must be accounted for in precise positioning systems and gravitational measurements. The atmosphere also experiences tides, with air pressure varying slightly due to the moon's gravitational pull, though thermal effects from solar heating dominate atmospheric tides. Some studies suggest correlations between lunar phases and various terrestrial phenomena, from earthquake timing to animal behavior, though many such claims remain controversial and require more research to establish causal links. What is clear is that the moon's presence affects Earth in myriad ways, some obvious, others subtle, all stemming from the fundamental gravitational connection between these two worlds. This interaction has shaped Earth's evolution, from determining day length and seasonal stability to possibly influencing the development of life itself through tidal pools where organic chemistry could concentrate and react. The moon's influence extends far beyond the silvery light it casts on a clear night, woven into the very fabric of our planet's nature. The moon's soil could be toxic to humans. The fine lunar dust that makes up much of the regolith presents potential health hazards for future lunar explorers. The dust particles are extremely sharp and abrasive because they've never been worn smooth by wind or water. Apollo astronauts reported that the dust clung to everything, penetrated spacesuits, and caused problems with seals and mechanisms. More concerning, the dust is extremely fine, similar in size to particles that can penetrate deep into human lungs, and its sharp, angular shape could cause respiratory damage similar to inhaling asbestos or silica dust. The dust also carries static electrical charge due to solar wind bombardment, making it stick to surfaces aggressively. Unlike Earth's soil, lunar regolith has never been exposed to organic material or biological processes, so its effects on living tissue are not fully understood. Some samples exposed to cultured cells in laboratories showed cytotoxic effects, damaging or killing the cells. The dust also contains tiny glass particles created when impacts melt and rapidly cool rock. Long-term exposure to lunar dust is a significant concern for future lunar bases, requiring careful management, including airlocks to prevent dust from entering living quarters, specialized suits that shed dust effectively, and possibly wet cleaning systems since the dust is too fine for conventional filters. Understanding and mitigating lunar dust hazards is essential for establishing safe, long-term human presence on the Moon. The Moon has been struck by many asteroids throughout history. While Earth's atmosphere burns up most incoming meteors before they reach the ground, the Moon's lack of atmosphere means every object, no matter how small, impacts the surface at full cosmic velocity. These impacts create craters ranging from microscopic pits on individual dust grains to basins hundreds of kilometers across. The largest impact structure, the South Pole Aitken Basin, spans roughly 2,500 kilometers across and reaches depths of up to 13 kilometers, created by an impact so massive it may have excavated through the entire crust to expose mantle material, though this interpretation remains under study. Scientists estimate that the Moon experiences about 1 ton of meteoric material impacting its surface each day, mostly tiny particles that create microcraters in the regolith and exposed rocks. Occasionally, larger impacts occur. In March 2013, a boulder-sized meteor slammed into the Moon with enough energy to create a flash visible from Earth without a telescope, the brightest impact ever recorded on the lunar surface by monitoring programs. These ongoing impacts continue to churn and modify the regolith, a process called impact gardening that mixes the surface and affects how lunar soil evolves over time. Each impact, whether massive or microscopic, adds to the Moon's collection of foreign material, incorporating samples from asteroids and comets into the regolith, creating a natural archive of materials from throughout the solar system embedded in the lunar surface. The Moon has no seasons. Earth's axial tilt of 23.5 degrees creates our seasons, as different hemispheres tilt toward or away from the Sun throughout the year. The Moon's axis, by contrast, tilts only about 1.5 degrees relative to the plane of its orbit around the Sun. This nearly upright orientation means that the Sun's rays strike any given latitude at essentially the same angle year-round. A region near the lunar equator always sees the Sun at roughly the same maximum altitude in the sky, and polar regions remain always in twilight, with sunlight skimming horizontally across the landscape. This lack of seasons has profound implications. Polar craters never receive sunlight, their interiors remaining perpetually frozen at temperatures barely above absolute zero, creating the cold traps where water ice can survive for billions of years. Conversely, some crater rims and mountain peaks near the poles experience exceptionally high illumination, with certain locations receiving sunlight for large portions of the lunar year. These so-called peaks of eternal light, or peaks of near-eternal light, could be ideal locations for solar-powered lunar bases, greatly reducing the challenge of surviving the 14-day lunar night. The lack of seasons also means the Moon's thermal environment depends primarily on local illumination rather than time of year. A location in sunlight bakes at over 100 degrees Celsius, whether it's January or July on Earth's calendar. The same spot in shadow plunges to negative 170 degrees Celsius. The Moon's climate, if it can be called that, is determined by light and shadow, not by orbital position, making it a simpler but harsher environment than Earth's seasonal cycles. The Moon influences biological rhythms. Many organisms, from marine creatures to mammals, have evolved behaviors synchronized with the lunar cycle. Corals release eggs and sperm simultaneously during specific lunar phases, ensuring that reproduction occurs when tides bring the gametes together. Certain species of fish, including grunion in California, time their beach spawning to high tides associated with full or new moons. Sea turtles often lay eggs during full moons, possibly using the bright moonlight to navigate back to the ocean after nesting. Some insects and birds may use the moon for navigation, and studies suggest that many animals' circadian rhythms are affected by moonlight levels. The evidence for lunar influences on humans is more controversial. Some studies report correlations between lunar phases and sleep quality, with people sleeping less deeply around the full moon, though other research fails to replicate these findings. Claims of increased hospital admissions, accidents, or births during full moons have not been so consistently supported by data when large statistical samples are analyzed. The idea that the moon affects human behavior is ancient, embedded in language through words like lunacy and lunatic, derived from the Latin word for moon. While the moon's dramatic gravitational effects on ocean tides are undeniable, its influence on human biology and behavior remains a matter of scientific investigation, complicated by confounding factors and the human tendency to notice patterns even when they don't exist. What is certain is that the moon has profoundly influenced human culture and imagination, if not necessarily human physiology, shaping myths, calendars, and the way we perceive our place in the cosmos. Our companion will eventually meet one of several possible fates. Looking billions of years into the future, the Earth-Moon system faces uncertain endings. Currently, it moves away from Earth, but theoretical models suggest this process could eventually reverse under specific conditions. The reason relates to solar tides. As the sun gradually brightens with age, some models predict it might spin up Earth's rotation rate through solar tidal interactions over timescales measured in tens of billions of years. If this occurred, and Earth rotated faster than the orbital period, tidal forces would reverse, pulling our satellite back toward Earth rather than pushing it away. It would spiral inward, eventually either breaking apart when it reaches the Roche limit, about 18,000 kilometers from Earth, forming a ring system, or colliding with Earth in a spectacular impact. However, this scenario will almost certainly never occur, because the sun will become a red giant in about 5 billion years, long before any such tidal reversal could happen. The expanding sun will likely engulf both Earth and its companion, or at minimum render them molten. If Earth somehow survives outside the sun's expanding envelope, the satellite might be torn away by tidal forces from the massive red giant sun, escaping into its own solar orbit. Either way, the cosmic partnership forged 4.5 billion years ago will end when our sun exhausts its nuclear fuel. The moon has inspired countless artistic works, from ancient cave paintings depicting the moon's phases to modern science fiction films imagining lunar colonies. The moon has fired human creativity across cultures and millennia. Poets have used the moon as a symbol of beauty, mystery, transience, and romance. Shakespeare referenced the moon dozens of times in his works. The moon appears in countless songs, from Moon River to Blue Moon to walking on the moon. Classical composers created pieces inspired by lunar imagery, such as Beethoven's Moonlight Sonata and Debussy's Clair de Lune. Visual artists painted the moon in every style from realistic to abstract, capturing not just its physical appearance, but the emotions and ideas it evokes. The moon features prominently in religious art from many traditions, from Islamic crescents to Christian nativity scenes showing the moon accompanying the Star of Bethlehem. In science fiction, the moon has been a destination, a resource, a stepping stone to the stars, and occasionally a threat. Jules Verne imagined launching people to the moon from a giant cannon in his 1865 novel. Georges Méliès created the iconic image of a rocket hitting the man in the moon's eye in his 1902 film. The Apollo landings transformed the moon from an unreachable celestial object into a place humans had actually visited. Yet this achievement only seemed to increase rather than diminish the moon's power to inspire. The moon continues to appear in art, literature, film, and music, an eternal muse that connects modern creators with their ancestors, who gazed at the same silver disk and wondered. Modern spacecraft orbiting our satellite have created topographic maps with resolution measured in meters, showing every major crater and mountain across the entire lunar surface. NASA's Lunar Reconnaissance Orbiter, operating since 2009, has photographed the entire surface at high resolution, captured thermal maps showing temperature variations, measured surface radiation levels, and detected hydrogen signatures indicating water ice locations. Japan's Kaguya mission created high-definition video of lunar terrain and mapped gravitational anomalies revealing mass concentrations beneath the surface. India's Chandrayaan missions provided chemical composition data and confirmed water ice at the poles. China's Chang'e missions have explored both near and far sides, with rovers analyzing soil composition and radar probing beneath the surface. These combined efforts have made the moon one of the best mapped objects in the solar system beyond Earth. Scientists can access elevation data for any lunar location, examine rocks and soil composition from orbit, calculate illumination patterns to find the best locations for future bases, and identify resources like water ice and useful minerals. This wealth of data transforms mission planning from educated guessing to engineering precision. Future lunar explorers will arrive knowing the local terrain in detail, aware of hazards like boulder fields or steep slopes, and equipped with knowledge of local resources. The moon that once was a distant enigma has become a characterized world, its geography as well known as many regions of Earth, ready to be explored, utilized, and eventually inhabited. As the soft glow of lunar knowledge settles around you, let your mind drift across the ancient surface we've explored together. Imagine standing on that grey landscape beneath the black sky, Earth hanging overhead like a blue and white jewel, the only colour in an otherwise monochrome world. Beneath your feet rests rock older than life itself, soil formed from 4 billion years of impacts, each grain touched by photons from a sun that has barely changed since the moon was young. The craters surrounding you tell stories of violence transformed into stillness, kinetic energy turned to permanent sculpture. The horizon curves sharply, betraying the small world you stand upon. And beyond that curve lies more of the same. Craters, plains, mountains, all waiting in airless silence. This moon we've journeyed across tonight is both familiar and alien, our oldest companion yet forever separate, close enough to shape our tides, yet far enough to remain mysterious. It was born in fire and has cooled to stillness. It was once closer and is now drifting away. It has watched Earth evolve from molten hell to living world, witnessed the rise and fall of countless species, and will continue circling long after humanity has either spread among the stars or returned to dust. The moon asks nothing of us, but offers its light freely, illuminating our nights and our imaginations, a silent partner in the cosmic dance that has defined our world since its beginning. Let that light guide you now into peaceful rest, carrying you on gentle tides of sleep toward morning. Good night.